So we will directly continue with a presentation being held from Jan Berger. Jan Berger is the founder and CEO of Themis Foresight, and he's presenting his views or his considerations regarding sustainability and the green future. The concrete title of his presentation is Quantum Green: How can quantum computing help to achieve the UN climate goals? So the virtual stage is yours.
Thank you very much. Just double checking, can you hear me?
Yeah, we can hear you very good.
Okay, wonderful. And I hope that my presentation is coming in as well.
Not yet, but it will come any second, I guess.
That's what I hope too. It should be.
Yeah, now we can see it. Perfect. Yeah.
Okay, wonderful. All right, so now you see the title. Okay, well, it's late in the game. We have until 6:15, something like that. And I kind of feel like between a rock and a hard place, because on the one hand, Jörg has asked me to go light at the end of this day. So I guess any discussion on how to beat the Landauer limit will be off limits for my presentation. Sorry for the physicists among you who like to debate that issue. And the other challenge that I have is that for this final talk, I'm moving into the realm of vision, and visions are a funny thing. I mean, they're hard to prove. So take Ray Kurzweil, for example. 15 years ago, he postulated that the singularity is near. Next year, he's going to postulate that the singularity is nearer, and it's well nigh impossible to prove any of his points. And normally, I don't like to move in that realm very much, as my company, Themis Foresight, engages in corporate foresight. So our clients kind of need to rely on a very high probability of the scenarios that we're painting. So usually our slides, therefore, look like this slide. But as I said, I'll try to go light and see how we can go through this. So we, as Themis Foresight, had a very, very interesting and fruitful collaboration with Bundesdruckerei. It's the federal print shop of Germany. Obviously, they print the money, but they also do a lot of stuff on cybersecurity. And Manfred Peschke and his team really do carefully look into the potentials of quantum computing in all sorts of different areas. So we had a very fruitful collaboration, which emanated in this report that you can see on the top left. I cannot share this report yet, but I can promise that in the first week of June, it will be available for free. So stay tuned and post it, or contact me via LinkedIn if you want to get the report a little later. It is unfortunately in German, but that's what happens when you work with German clients. We will probably provide a translation later on in the year. So looking at this whole field of quantum, we do anticipate investment on the order of 103 billion by 2040. There has been a lot of progress made in quantum computing, demonstrated quantum supremacy, lots and lots and lots of applications already underway solving combinatorial problems, like the traveling salesperson problem. Microsoft has announced that they are close to a breakthrough on topological qubits. If that is true, and then if that breakthrough will come in the next couple of years, that will certainly change the landscape for hardware solutions around quantum computing. The difficult part is going to be anticipating 2030, 2040, 2050, and where we will be with quantum computing then. looking back at the last 2 years, this is pretty much what the world felt like. All the news were dominated by COVID. If you look at the news today, this is what the world feels like if you live in the Western Hemisphere. And without belittling any of the horrors that the Putin regime and in Russia are causing right now in Ukraine, we must not lose sight of what the world globally is like or looks like. So we've got fires in California. We've got people being displaced because of floods in countries that are close to the sea, rising ocean levels. We have massive drought all over the hotter parts of the world. Some of you may have seen that just a couple of weeks ago, temperatures in India were measured of 61 degrees Celsius. And what it will produce is not just, fairly nice and benign protests like Fridays for Future, but it will produce mass migration, possibly further wars, and it could produce mass hunger. So the real question is, and that's also how we framed that report or framed a section of the report, can quantum computing contribute to solving the global problems that we have? The global problem is, by the way, not saving the planet. The planet will save itself. It's more the question of will we be able to keep the planet habitable for humankind? So looking at energy consumption, I mean, there's this whole discussion right now, which has been going on for the last 2 to 3 years, of green IT and the massive energy consumption that computing processes start to take on. Certainly, the world of cryptocurrency has done its share to raise awareness of the massive energy hunger of computing operations. So if we look to the year 2030, there are a lot of statistics that point to fairly realistic expectations that global computing power will have an energy demand in 2030 of 331 terawatt hours. By comparison, today, we have a global energy demand for computing of 114 terawatt hours. So we're going to triple energy demand for computing globally in the next 8 years. Just looking at the properties of quantum computing as it exists today, we're talking about quantum annealing. We can probably offset some of these effects by 10%, which would be 30 terawatt hours, or the annual energy consumption of today of countries like Nigeria, Morocco, or Serbia. So that alone should be an incentive to go into quantum computing. Furthermore, optimizing traditional industrial processes, which are energy intensive, will have its share to contribute to a reduction of energy demand. So just to give an example, electricity production currently loses roughly 60% due to transformation from one energy carrier to the electricity output. There have been very effective tests in the area of solar energy where electricity transformation has improved by 25% thanks to quantum computing. I also know for a fact that a number of energy companies like E.ON in Germany already use quantum annealing for optimizing grids and reducing energy loss. And just by way of comparison, if we manage to optimize transportation globally by only 8%, this would already offset the entire global energy need for computing. So there are a lot of areas where great companies like IBM, D-Wave, Fujitsu, and others are already working with annealing technology to solve the traveling salesman problem. If we scale that, we can certainly reduce energy demand. If we go into other areas where quantum computing can play a role, now every one of us consumes food that is based on using fertilizers on fields, be it as a secondary effect, i.e. food that feeds the cows or the pigs that we consume as fine steaks later on, or whether it's direct consumption of grain. All these fertilizers are being produced using the, by now, I think 130-year-old HABER-BOSCH industrial process, which, by the way, contributes up to 2% of global emissions. Now, this is sort of the vision part. This is total speculation. There are nitrifying bacteria on the ground of the sea, and if we manage to use quantum computing for deciphering the metabolism of these nitrifying bacteria and figure out how to produce nitrites or fertilizer without using these giant pressure cookers as depicted right now, that could be a global industry that could operate emission-free. So, as I said, you should take that with a grain of salt. We're in the realm of speculation, but this is definitely an area where I think, or where we think, quantum computing can be applied. Same with material science. Most of the materials that we need to replace concrete or steel, or even to optimize concrete or steel, work with on a physical level. It's quantum physics essentially. So we're trying to calculate and optimize quantum physics using silicon computers. It might be, or it will be, a lot easier to have a quantum computer figure out quantum materials or quantum physics. So there's a whole other area of application, and certainly there are already by now lots of ideas for how to use the fact that quantum machines are probabilistic to anticipate negative outcomes of experiments in the pharma industry, saving not only a lot of money and a lot of R&D time in life science areas, but on top of that, lots and lots of lab mice could be sorted. And as an insider joke, it might have the added benefit that mice can stop observing us and we might observe them, for those who've read The Hitchhiker's Guide Through the Galaxy. I do want to briefly touch on, now we're moving further into the timeline. So we're talking 2040s, 2050s maybe. There is a digitization, and a lot of the evangelism that came out of the Silicon Valley in the last 10 years has mystified data to a point that we have come to wrongly accept a false truth that the more data we have, the more we know. I'd like to challenge that. Data per se is super stupid, and then piling data on top of data and having a few algorithms run over it does not necessarily generate actual knowledge. As it is right now, this is the Google data center in Dallas. A river was partially diverted to run the cooling. Dallas, Oregon, not Dallas, Texas, was run through it to to contribute to cooling. right now, estimates are that 80% of the data stored in data centers worldwide are completely useless and are not being used. So there's a whole, it's like a whole string in the consulting industry has already started working on helping companies how to reduce data storage of data that they don't even need anymore. So this is kind of how ridiculous it has become over the last 10 years. Projecting or looking a little bit into the future and at some of the properties of quantum computing, if in the future what we need is brain power, sort of, talking quantum AI or quantum artificial intelligence, then in other words, if we want computers to emulate brain functions, then we will need to move into a different discussion of data flows and data storage. It is a misconception to think that our brain consists of a processing unit and data storage. That's not how our brain works. From what we understand, how our brain works is that there is a continuous flow of data and synapses connected to useful things like thought, creativity, anticipation, and other functions that'll help us survive as human beings or as mammals, essentially. Now, the interesting thing is our brain has a power of roughly 100 teraflops. It a little bit depends on size. And for that, it only needs 20 watts of energy. If you compare this to, so in other words, we have a ratio of 5 flops per watt being used for brain power. If you take a Tianhe supercomputer and you use the same metrics, i.e. it consumes energy of 24 megawatts and has a flop rate of, I think, 33 or 38 petaflops. You have currently a rate of 0.0015 flops per watt. So that's like how much energy we actually waste by using supercomputers. If we can leverage quantum computing to the point of reducing the energy input to an output of flops as we currently have with our brains, there will be massive energy reduction, and what we detail a little bit in our report are a number of initiatives that work on quantum data storage, quantum computing, and the different types of data flows for the future. So we're now kind of in the year 2050. But that could be a formulated goal for a quantum vision of massive energy reduction. And I'll just leave it at that. It is 6 o'clock. At the end of the day, future is what we make of it. And I hope everyone, gets to enjoy a nice evening. So much from my end. Thank you.
Thanks a lot, Jan Berger, for this very, I would say, interesting final speech, final presentation of the day, which was very good, concluding the very interesting day.